workshop. Thank you. Hopefully will do my best to contribute. So I'm going to speak about Riemann-Hilbert problems, and the first half hopefully will be really an introduction. So perhaps too basic for a lot of say friends in the audience, but there's no going back now. But just for starters, here's Stirling's approximation from Wikipedia. N factorial is described by that quantity on the right-hand side. And of course, that's what they mean by the squiggly equal sign or limits like that. You take the n factorial, divide by the explicit quantity and take a limit, and you get 1. Okay? So, and the reason that one way to prove that is to use this amazing formula where you represent n factorial as an integral. All right, so in a nutshell, a lot of what you will probably hear about over the next, maybe tomorrow and other days, if you hear Riemann-Hilbert problems in the title, is an amazing formula which represents something of great interest in areas of mathematical physics in terms of something that's not an integral but is a solution of a Riemann-Hilbert problem. So I thought I'd just start with that, very simple example. What's a Riemann-Hilbert problem? So the goal is to find a function or find a collection of functions. Okay, so that's the problem is to find f, and I can't resist. It's right there. It's right there. And what are you given? You're told that the function f is analytic off of some collection of contours. So I drew the most complicated collection of contours I could make the computer draw for me. Sigma is the contour. They all have orientations on them. And omega represents the complex plane. Take away those contours. And if I did it right, the plus and minus subscripts on omega mean that you're either on the minus boundary value of the contour or the plus boundary value of the contour. And so what you imagine is skier's left is the plus boundary value. So you traverse the contour according to orientation. On your left-hand side should be the plus boundary value. So this omega subscript plus means the region of the plane on the plus boundary value of this contour. And I drew them consistently. So over here as well, this is the plus boundary value. Okay. Sometimes you can draw contours that don't obey that, but this one did. Okay. So you're given the contour. You're given a function little v on the contour, and you're looking for capital F. It's analytic off of the contour. It's usually given some simple asymptotic behavior at infinity, like 1. So 1 plus an error term as z goes to infinity. And it has good boundary values if you let z approach the contour. From the plus or the minus side, those boundary values are f plus and f minus. And they're related by this. Okay, I wrote down a multiplicative version of the Riemann-Hilbert problem. F plus equals f minus times this function v. And that's supposed to be true for all points c in the contour. Okay, that's the first example of a Riemann-Hilbert problem. Find f. Okay? And of course, I picked the function v to be scalar. And so the solution is take logs and then use something called the Cauchy-Plomelj-Sochatski formula, which is written here. So it's basically the Cauchy transform of the log of v, and then you have to exponentiate to get back to the function f. So that's the first example of a Riemann-Hilbert problem and its solution. Okay. Now you look at that and you realize, oh, well, technical issues are going to arise if the contour goes off to infinity. I'm going to need to know that this integral is convergent, and I'm going to be worried about winding numbers, that kind of stuff. Okay, so those are all technical issues that arise even when you're dealing with a scalar case. But what I want to talk about is not the scalar case, because that's sort of very classical. Okay, so note f and v are scalars, and in general, what people are studying when they study Riemann-Hilbert problems in the context of this conference maybe is matrix-valued Riemann-Hilbert problems. Okay, and so I have a couple of examples of that, and they will be in applications first to integrable partial differential equations. So here's the first example of a matrix Riemann-Hilbert problem. The contour is the real axis, and I wrote down just the jump matrix. So it's now a matrix given by a function R0 on the real z-axis, okay? So, okay, it's 4 entries. I suppose I should read them all, but you can see them all there, right? Depends parametrically on x and on t, but the complex variable in the problem is z, okay? And this function is defined for z real. But because it's matrix valued and we're trying to factorize this on the real axis, taking logs turns out not to be very useful. So let me write down the Riemann-Hilbert problem. I just wrote down the jump matrix, but right there on the left-hand side is the problem. Find m. We're looking now for a 2x2 matrix valued function. Each entry is an analytic function of z off of the real axis. So it's analytic in the upper half plane. Each entry is analytic in the lower half plane. And it has good boundary values on the real axis. So m plus represents the boundary value from above. M minus represents the boundary value from below. And m plus is related to m minus by that jump relationship there. Okay, so you really think I'm taking v and I'm trying to factorize it into an analytic function above times the inverse, okay, m minus, right? I'm factoring the jump matrix v into a product of two things that are analytic above and below the real axis. And it has to be normalized, so here's the normalization. The matrix M converges to the identity matrix as z goes to infinity. Okay? So problem is to find M. All right? That's the second example of a Riemann-Hilbert problem. And if you can find M, then it turns out it will have actually better than asymptotics like this. The first term is the identity matrix. And then there's a 1 over z term, and the matrix looks like this. 0, IQ, negative IQ bar, 0. Plus corrections of order z to the negative 2. And those were the parameters x and t in the jump matrix that I defined on the previous screen. So let me go back just so you see that there's x and t in here. There's a t and there's an x. It looks kind of Fourier-ish, right? Okay, if you can find the solution, it has this form. And that means the first moment at infinity is just a function of x and t. And turns out that it solves this nonlinear partial differential equation, which is the defocusing nonlinear Schrodinger equation. Okay? So that's, in a nutshell, how Riemann-Hilbert problems can be connected to integrable nonlinear PDEs. And I'm skipping all of the magic. There's a huge amount of magic, which is that there is a transformation from potentials Q, initial data for this nonlinear partial differential equation, to a reflection coefficient. And this transformation is amazing, so that as Q evolves according to the nonlinear PDE, the reflection coefficient evolves in this very simple way, multiplication by e to the 4i z squared t. So I'm skipping all of that magic, which is really the direct and inverse spectral theory of the nonlinear Schrodinger equation. And in this instance, the lax pair was discovered by Zakharov and Shabbat in the early 70s. And the spectral theory of one of those operators leads to this transformation, this spectral transform that produces the reflection coefficient. And the Riemann-Hilbert problem accomplishes the inverse direction. Okay, given the initial data, you compute the reflection coefficient. That evolves very simply in time. And then at a later time, you solve this Riemann-Hilbert problem to extract the potential Q solution of the nonlinear Schrodinger equation. And I should say there are other ways to accomplish the inverse problem that have to do with systems of singular integral equations that are, essentially equivalent to the Riemann-Hilbert formulation I wrote down up there. So what I've just showed you that there's some way to characterize solutions of nonlinear Schrodinger equation by solving Riemann-Hilbert problem, okay? I have this button I can push. So here's another version of a Riemann-Hilbert problem. This one turns out will characterize the focusing nonlinear Schrodinger equation. I put it up in its full glory because I want to talk about a little bit about poles. So the problem is really the same sort of problem. You want to find M, which is a 2x2 matrix valued function, analytic above the real axis and analytic below the real axis, with one additional assumption. We're permitted now to have poles in the complex plane. Poles in general are going to be in the upper half plane, and then their complex conjugate poles will be in the lower half plane. So I really should say it's meromorphic in the upper half plane, meromorphic in the lower half plane, with poles at prescribed locations. So there's a set of finite number of poles, z1 through zn. And okay, so the function m still has good boundary values on the real axis, and the boundary values are related by this m plus equals m minus times v, the jump relationship, very similar to what I had on the previous couple of slides. But there's an additional statement, which is that, oh, okay, there's a pole at zk, and this kind of funny-looking statement here explains the residue of the pole. And it says that if you read this on the left-hand side, the residue of the matrix at zk is given by the right-hand side. And if you compute the right-hand side, you'll find that, okay, there's zeros in the second column up here. And that means that the matrix M has no poles in its second column at zk. And the residue in the first column is related to the value of the matrix M at zk in the second column. Okay? So it's an implicit description of how poles occur. All right? And so, you know, if you're looking forward, each pole will correspond to a soliton, a solitary wave solution of the nonlinear Schrodinger equation. Okay. Well, so this introduction, it's a grotesque, perhaps looking meromorphic Riemann-Hilbert problem. Find M satisfying all of these conditions. If you can find it, then in the large Z expansion of M, there is a term which depends upon x and t, and that solves the focusing nonlinear Schrodinger equation. So the two differences between the defocusing and the focusing were the sign of this jump relationship up there. I've killed the pointer. The sign of this jump relation, the plus there, and there's poles. Okay. So I'm still giving examples that characterize things. So the third example is the Korteweg de Vries equation. And so it's now perhaps getting tiresome, but we now look for a vector M. Okay? M is a 1×2 matrix. Each entry is analytic in the upper and lower half plane, and it converges to the normalized vector 1, 1 as z goes to infinity. Has this jump relationship here on the real axis. It has poles of a very similar form at locations lambda 1 through lambda n, and they're complex conjugate poles in the lower half plane. So basically, very similar looking problem, except that the x and t dependence is a little different, right? There's a z cubed times t there. That's really the only major difference in the jump relationships. Okay, and then, so it looks small, but I just rewrote the Riemann-Hilbert problem up there, okay? If you expand the solution as z goes to infinity, you get a row vector m1, and the first entry of that row vector, take a derivative of it, it solves the Korteweg de Vries equation. Okay, so again, I'm skipping the beautiful connection, which is where this reflection coefficient comes from. It comes from scattering and inverse scattering theory of the one-dimensional Schrodinger equation. I'm just skipping all of the beauty of that in order to give examples of Riemann-Hilbert problems, but it accomplishes the inverse problem, going from the evolved reflection coefficient back to the potential. Okay, so maybe before that one, it's worth saying, what do you do with this? So here's a couple of questions that people can use Riemann-Hilbert problems to answer. What's the long-time asymptotic behavior of any of these PDEs? They're not linear, so you would run into problems if you were to use a Fourier-based method. Maybe you want to put a parameter in front of the third derivative term there and study the behavior when this parameter goes down to 0. Or maybe you would like to take some crazy singular limit of one of these PDEs. And the hope is you solve Riemann-Hilbert problem just as you might analyze an integral, try to extract asymptotic information about the solution of the Riemann-Hilbert problem, and from that pull out information about the solution of the PDE. That's the idea, okay? So next example is from a different area entirely. So orthogonal polynomials. There I've written down a polynomial of degree j, and I've got some extra parameters n floating around, but that's a polynomial of degree j, and I choose them to be orthonormal with respect to some measure of this form, e to the negative n v of x dx. It's also possible to define orthogonal polynomials with respect to a discrete measure, so this summation equaling either 0 or 1 is the analog of that integral equaling 0 or 1, except for I have a discrete finite set of nodes where I'm enforcing orthogonality, okay? Okay, and the interest, or an interest, some folks are interested in the behavior of the orthogonal polynomials when the degree n, or j on the previous screen, goes to infinity, and maybe there's a parameter capital N which is sitting in the measure, which also goes to infinity. And the goal is to provide a uniform asymptotic description anywhere in the complex plane for these polynomials. And here's just a few applications. We'll probably hear about more applications than these in the next couple of days. But of course, one of the reasons for interest in orthogonal polynomials recently has been, or maybe not that recently anymore, but studying asymptotics of statistics of eigenvalues for unitary ensembles of random matrices and their relatives. There's also very interesting work in the 6-vertex model in random tiling problems, last passage percolation, and total lattice and approximation theory, among other things. We'll hear more about them maybe. So for orthogonal polynomials, Fokas, Eats, and Kitaev made this discovery, and I've written down at the top of the screen the solution of the Riemann-Hilbert problem at the bottom of the screen. The problem is to find a 2x2 matrix that's analytic off the real axis. It has this funny-looking asymptotic behavior as z goes to infinity, and that's the jump relationship on the real axis, okay? And the solution is, okay, the first column contains polynomial of degree j and j minus 1, and second column is a Cauchy transform of first column times weight. Okay, so this discovery led to fantastic results about the asymptotic behavior of orthogonal polynomials through a Riemann-Hilbert analysis. Okay, and then there's a meromorphic version when it's a discrete orthogonal polynomials. I will just show you that to kind of disturb everybody. Sorry. Well, so the integral on the previous slide becomes a sum. And you have poles, and you characterize the poles by a residue condition. I'll just say that, okay? So those were examples of where Riemann-Hilbert problems can be used to characterize things from other areas. I guess the main ones were nonlinear partial differential equations and orthogonal polynomials at the end. So what do we do? So I wrote down, I put up here 4 useful small norm situations that hopefully give an intuition for how folks use Riemann-Hilbert problems to compute asymptotic behavior. Okay, so there's usually a parameter like n, which is going to infinity, or time, which is going to infinity, or some other collection of parameters. You want to understand behavior of solutions when those parameters are getting stressed. Okay, so here's the first guiding principle. If you're interested in Riemann-Hilbert analysis, and it is this statement. So if you look for a matrix that's analytic in the plane, and it goes to identity at infinity, okay, Liouville's theorem tells you that the only solution of that problem is that M is the identity matrix everywhere. Okay, that's 0th order guiding principle. Okay, the next one is a perturbation of that. So suppose I'm looking for a 2x2 matrix. It's analytic in the plane, except across some contours. So up there it should be complex plane, take away some contour sigma. It goes to the identity matrix at infinity, and the jump relation m plus equals m minus, I've written it as identity plus e. So if e were 0, then it would be saying that across the contour m plus equals m minus, which means that actually m is analytic across the contour. So if I had e was 0, I would just have an entire function that goes to identity at infinity, and it would then be the identity matrix. The statement is, if I know that this E is small in some sense, either L2 or L infinity, if I know that it's asymptotically small on the contour with enough regularity, then I can prove that a solution to that problem exists, okay? And I can prove that it's basically close to the identity matrix everywhere. Now, this clearly looks vague, right? Does this depend upon Z? What does this mean? So I made that vague because the sense in which M is approximately the identity matrix depends upon how strong the information you have about the norm of E is. Okay? The best possible case is that M is uniformly close to the identity matrix everywhere in the plane, and for that to happen, you have to have very good regularity on the size of E. Okay? So that's really the fundamental guiding principle in Riemann-Hilbert analysis, in asymptotic analysis of Riemann-Hilbert problems. And what you try to do is start with some given problem. Find A, and it's nowhere near as simple as what's in the green box. Your problem is to find A solving some Riemann-Hilbert problem, and then you make a sequence of explicit transformations from A to B to D, and eventually, by explicit transformations, you arrive at a problem where the unknown is now M, and you you check that the M satisfies something along the lines of the green box. You compute, you know that M exists. You work backwards, you get asymptotic information about the original problem. That's in a nutshell how things are supposed to work. And it is the art of going through these transformations that has developed over the past 30 years or so, with amazing connections to other areas of mathematics just to accomplish these sequence of transformations. Each time you start a problem, you know, the kinds of calculations that people in this room have done have required, you know, all sorts of different results, from classical algebraic geometry through to approximation theory. Okay. Yeah, there's one more, which maybe I'll say quickly. Suppose you have a function, you know this, you have a matrix, the entries are smooth in the plane, and it converges to the identity matrix in the plane, so I'm no longer saying it's analytic, it's just smooth in the plane, okay? And I know that M solves this sort of elliptic PDE. D bar derivative of M is equal to M times W. So D bar is this differential operator. It annihilates, so it's that, okay? If you check it, D bar kills all analytic functions. So if you have a problem in which the D bar derivative of M is equal to M times W, and you know something about this, the solid two-dimensional Cauchy transform of W in the plane, if you know that that's asymptotically small, then you can again prove that M exists, and in L infinity it's close to 1, close to the identity matrix. So the reason I say this is because this sometimes allows people to find transformations that break analyticity, but use harmonic analysis techniques to control the error term. Okay, so this observation opens up the collection of transformations to leave the class of analytic functions. Okay. I want to talk about this work, but maybe it's useful to give one very simple example, okay? So let me go back. I think I have a couple of minutes to do this, right? So on the screen is the Riemann-Hilbert problem for the defocusing nonlinear Schrodinger equation. I need the jump matrix, actually. So that's the jump matrix for the defocusing nonlinear Schrodinger equation. And let's suppose that t is equal to 0 for a second. And I ask the question, Okay, how do you show that the potential, which is determined by this jump matrix, how do you show that that goes to 0 when x goes to infinity? Okay, so I remind you the potential is obtained by looking at the large Z asymptotics of the solution of this Riemann-Hilbert problem. Maybe a simpler version of the question is, can I prove that if x is large, maybe large and positive, can I prove that M is close to the identity matrix everywhere? Okay? So there's like 1 or 2 steps to see that. All right, so T is 0, so I should rewrite this jump matrix. I'll try to do it so it's legible, okay? Negative 2yzx. So if you multiply those two matrices together, do you get that matrix? Did I do it right? Yeah, yeah. So this represents, this is the jump relationship that's up there on the screen, okay? T is 0. I said T equals 0. Is cool? So now I want to make an assumption that will simplify this. I'm going to assume that R0 is something real and analytic, so maybe like 1 over 1 plus z squared to the power of 5 or something like that. So some analytic function that will simplify the calculations, okay? So I want to take this term and move it over here, and then rewrite this. So M times 1, 0, negative R0 e to the 2I zx 1, okay, plus boundary value, equals M 1, 0, negative R0 bar e to the negative 2I zx 1, minus boundary value over here. So you guys saw what I did, right? I put the plus boundary value outside. So I'm assuming, I'm really using the fact that R0 is analytically extendable above and below the axis a little bit. Okay, so the next, the one step to do, here's the real axis. Okay, and then let me draw a little strip above and below the real axis. And I'm going to define A is just equal to M if I'm outside of this little strip, either above or below. Okay, so A is equal to M. And inside here, I'm going to take A to be the left-hand side of that quantity. So A is M times that matrix. The negative. Let's go put dot, dot, dot. You know what I mean. It's that entry up there. Down below, in here, A is M times that matrix. Okay? So I've defined A everywhere in the plane. It's either equal to M or it's equal to these crazy products. So now A should solve its own Riemann-Hilbert problem. Right? Analytic in the plane, take away 3 contours. It goes to the identity matrix at infinity because, well, M goes to the identity matrix at infinity and R0 goes to 0 at infinity, so that didn't screw that up. Okay? So I should write down a Riemann-Hilbert problem that A satisfies. And I'm only going to write, yeah?
How do you understand this, again, R0? In your slide, conjugation goes up to Z.
Yes?
Your nice function R0, if you put bar,
Yeah, would be bad.
then it's not like the function. Yeah, the same story.
Right, so let me,
From the interpretation of conjugation, just could explain.
Yeah, so this is a formula which is true for Z real. So it's really the, right, so that's a formula that's true for Z real. Hold on, so it's a formula for Z real, and if I choose my function R0 to be real for Z real, then R0 bar is equal to R0. And so I just use the same function, right? I'm not using here, I'm not using the extension of R0 of Z bar. I'm just using the extension of R0 bar. Yeah, I agree. You're right. I should be more careful about that. Yeah, okay. So maybe let me try to write here negative 1 over 1 plus Z squared to the 5th. Right? Thank you. Sorry about that. Okay. What am I doing? Oh, yeah. Okay. So if you check the jump for A plus equals A minus on the real axis. So you have to check that, but I've exactly factored it so there's no more, the jump matrix on the real axis is now the identity matrix. Up above, the relationship on this contour here is A plus equals A minus times the triangular matrix that I will not remember. Probably it's R0 e to the 2I zx. And then down here on this contour, A plus equals A minus times negative. Does that look right? So A plus is M, and if I want to multiply A minus along this contour, I have to multiply the inverse of this matrix. So the jump should be with positive R0. Down below, A plus is actually this, and if I take A minus, I need to multiply by this matrix to get the jump correct. So I probably wrote it correctly. I don't know if it's legible for anybody, but that's okay. That's the Riemann-Hilbert problem for A is find A. It's analytic off of those two contours, and it has identity asymptotic at infinity. But now the jumps look like this. Okay? So if x is going to plus infinity, then what I need to do is look at the exponential. So e to the 2I zx is going to be e to the 2I times x times, let's say z is u plus iv. So I got lucky, it works, right? So there's e to the 2I xu times e to the negative 2 xv. So on the upper contour, if x goes to plus infinity, that's giving me exponential decay, right? And if I'm on the lower contour, the sign has changed, and so when x goes to plus infinity, I get exponential decay. So this means I'm now in the situation of the guiding principle. The jumps are identity plus exponentially small. I can prove by trickery that I haven't shown you that the solution to this problem, A, must be identity plus exponentially small corrections. And when you unravel that, you can actually deduce it. I won't do it here, but you can get that the potential is actually exponentially small. Okay? So here's a great, if you want to work on this or learn a bit about this, that's beautiful if x goes to plus infinity. But of course, it royally fails if you want to let x go to negative infinity. And that is where you need a trick, a better trick to study the behavior when x goes to negative infinity. It still is exponentially decaying, but you have to do some screwing around, maybe is that the proper term? Okay, so that's just one example of using the guiding principle, okay? Okay, so in the what time remains, I will not go over, I promise. I want to talk about work with Manuela Girotti, Tamara Grava, and Bob Jenkins. which has to do with one of the examples that I mentioned. So this is, okay, KdV equation. Suppose the reflection coefficient is 0, but there are exactly n solitons, and they're described in this way, okay? So I'm looking for a vector, which is analytic in the complex plane. It's meromorphic in the complex plane. It has exactly two n poles, n in the upper half plane on the imaginary axis, and in the lower half plane on the imaginary axis. And the residues are given up here, okay? Has a symmetry, which is m of negative lambda is m of lambda times 0, 1, 1, 0. And if I can solve this problem, then I'm producing an n soliton solution by extracting information at infinity in this way. Okay? I'm making assumptions that these n poles are living in an interval, in a window on the imaginary axis between I eta 1 and I eta 2, and they have a density function. So they're distributed relatively uniformly on the imaginary axis between I eta 1 and I eta 2. And the C's, so those, if you look back, there was this, each residue has a Cj in it. I'm assuming those are nice functions as well, and they look like this. Okay, the C's are really a discretization of a smooth function R1, okay, times scaling factors. All right? So my problem is n solitons. And I've normalized them in a bit of a funny way. And if each soliton were in a vacuum, so independent of the other solitons, then there's a way to figure out where is the center of the jth soliton. And it turns out that it would be centered at this location. Okay, so at t equals 0, it would be centered at this location. And that location looks normal, except that I've got a log n here. So basically, all of the solitons are centered at negative log n plus little shifts. And there are n of them. Okay? And the speed of each soliton is 4 times the absolute value of lambda j squared. That's in between eta 1 and eta 2, so it's, you know, some band of velocities. So it's a very regular gas of solitons. I'm hoping at some point to study random gases of solitons by, you know, this kind of crazy analysis, but right now it's a very regular gas of solitons. And so there's a picture in the plane. You see the interval I eta 1 to I eta 2 and its complex conjugate, and the x's are the locations of the poles. And the left-hand side is just a repeat of the meromorphic Riemann-Hilbert problem. Okay. The first thing we did, so there's a paper by Dyachenko, Zakharov, and Zakharov where they posited some new class of potentials called primitive potentials. And for that problem that they described, the primitive potentials are determined by 2 reflection coefficients. So we decided we would consider this and see if we could extract their Riemann-Hilbert problem in this case as a limit of that. So to get that as a limit of these very simple problems, okay? So the first thing is an approximation. I will not give a justification for this, but here's a Riemann-Hilbert problem that is no longer meromorphic, okay? It is seeking a function analytic in the complex plane away from two contours, so negative eta 2 to negative eta 1 and eta 1 to eta 2. And yeah, I wound up rotating the plane to get to this problem. And the jump relationship is given as described here on the contour sigma 1, which is this contour. The jump looks like that. On the contour sigma 2, the jump has this form, and the function r is related to r1 by that rescaling, okay? Okay, so it turns out that this problem for y is a valid approximation to the n soliton Riemann-Hilbert problem. And so the first thing that we did was prove that as n goes to infinity, un determined by that meromorphic problem converges to u, the solution of this problem here, right? Obtained from the solution of that problem. Now, the interesting thing is, when you work with solitons, they're exponentially decaying in both directions. But this function u determined by this new Riemann-Hilbert problem is decaying when x goes to plus infinity, but not when x goes to minus infinity. Okay, and this is just the initial data for the KdV equation. It's just initial data. So this is the behavior of that function u of x when x goes to negative infinity. And it's a classical genus 1 wave train, right? A genus 1 oscillatory solution of the KD of, well, it's a genus 1 potential, right? So maybe I won't go through what all the parameters mean, but each parameter is determined in terms of the function r and the endpoints eta 1 and eta 2, okay? So the important part of this slide is that there is an explicit asymptotic formula as x goes to negative infinity for the potential, and as x goes to negative infinity, it's just a periodic oscillatory function. It's not going to 0 at infinity, okay? You can rewrite it if you want it using the, what are they, the Jacobi theta functions. This is sort of a lost art, but Tamara Grava and Bob Jenkins both have resurrected this art in the, in their secret underground layers. Okay, so if you want to study the solution of the KdV equation with that initial data, then turns out that's what the time dependence looks like after rotating the coordinate axes in the complex plane. And this is the Riemann-Hilbert problem to study. And now, question, what is the behavior of the solution when t goes to infinity? Okay? So I have not written out the details of the Riemann-Hilbert analysis in that case, but there's a sequence of steps that you have to carry out. And firstly, oh yeah, so x over 4t is now a relevant parameter, and so that's going to be called xi. And the asymptotic behavior will depend upon the choice of xi. So here's a picture of the solution. So if xi is big, so bigger than eta 2 squared, then the solution is exponentially small. So that, remember, that means t is going to infinity, and x over 4t is bigger than eta 2 squared. Then the solution is exponentially small, okay? And if xi is in between eta 2 squared and some lower critical value, then the solution takes on this form, and it has, okay, it has, let me just say it's represented by an asymptotic genus 1 solution whose endpoints are evolving in the variable xi. Okay? And this is a picture. So when the parameter xi is near eta 2 squared, then it's a genus 1 solution where the band is like very close to eta 2 and negative eta 2. And if xi is down near the next transition point, then you almost have the full band between eta 1 and eta 2. Okay? And lastly, if xi is less than that critical value, then the solution is again described in the same way. Did someone else hear drums? It's described in the same way, except that the two branch points that define the Riemann surface that generates the theta functions are now fixed at eta 1 and eta 2. Okay? And this is a snapshot of the solution at very large time. So time is, and this is actually a cartoon. So time is large, and you see that if x is such that xi is bigger than eta 2 squared, the solution is 0. And then it's a modulating genus 1 wave train, and then when you hit this other critical value, it no longer converges to 0, but it just gives you a rather simple genus 1 solution for x less than this critical value here. Okay? Here are the steps in the analysis. You can see it was getting late at night when I was writing this. So just for this is really for those who are like experts in the room. The first step is to basically use some kind of a function g to isolate the contribution from these two intervals, and f gets rid of the reflection coefficient in favor of constant jumps. Okay, and then there's the canonical second step of opening up the lenses in very similar to what I described on the green boards. You finally arrive at a Riemann-Hilbert problem on this kind of a contour. Okay, and everything that is shaded is exponentially decaying. So this grayed out portion of the jump is exponentially decaying, Okay, that's exponentially decaying. So really, what is surviving after these what are relatively standard transformations is a Riemann-Hilbert problem with jumps on the real axis. And I just, for the momentarily, ignore all of the jumps on the contours in the plane and just concentrate on the Riemann-Hilbert problem that's left on the real axis, which I rewrote here. Okay, calling that P infinity because it's not directly related to any of the previous Riemann-Hilbert problems. Find a matrix, 2x2 matrix, which satisfies these crazy collection of jump relationships and has this identity asymptotics at infinity. And this is my last slide, I think. So really the analytical obstacle in our work was that we wanted, so I should go back and just say that. Here, I'm still looking for a row vector solution of this problem. And it just turns out when you're doing Riemann-Hilbert analysis, if you're looking for a matrix solution, you can build matrix approximations, and the algebra of controlling the error works much better. So if you're dealing with a vector solution, you have to get to a small norm jump problem, or else you're stuck. And in order to get to a small norm jump problem, you need a matrix approximation. So what we wind up doing is building a global matrix approximation to a solution to this Riemann-Hilbert problem. And the sticking point was that there are critical values of the parameters where no matter how you build this matrix solution, it's singular in one way or the other. So we had identified a solution, a matrix valued solution of this model problem, which worked except at one critical value of the parameter. And then we couldn't figure out how to get around that one critical value. Then we found there was another solution that worked in the neighborhood of that critical value of the parameter. So by patching together these two things, life is great, except that nobody wants to present that. So then, of course, we realized later that what we should do is allow for a singularity, and that's been done before, in fact. But we just built a solution that has, at every value of the parameter, a pole at lambda equals 0. And in order to avoid that pole, we exploited some symmetries to derive a small norm Riemann-Hilbert problem. So that was really the analytical obstacle that we finally overcame. Okay. Thanks.
Questions for Kelly? This theory probably works not only for so nice functions as scattering function,
Yeah.
scattering data.
Yeah.
If it's not meromorphic in a complex plane as this one, it is not even extendable beyond the real axis.
Yeah.
So
I'm really glad you asked. Yeah, this presentation.
you can put the
Yeah.
absolute value
Yeah.
with two vertical lines with Z. So what happens with them?
Yeah. So there's no difference. I mean, I used analyticity of the reflection coefficient just to make things simple. Okay. You can still do it. Yeah. There are let's say there are technical issues to resolve. So historically, the first way that you proceed is by rational approximation. You would approximate your function R0 by something rational, and then you leave a little residue on the real axis, but you extend off the analytic part. And what stays on the axis is small norm, and you control that by operator theory. Okay? That's one way to do it. And then another way, which I didn't want to go crazy, but you can also find extensions of a function R0 that are not analytic. So if you have that the function R0 maybe has one derivative, you can define a function in the upper half plane and lower half plane that is a continuous extension of that, or a differentiable extension of that function. And then, you have still small norm jumps, but there's a region where you no longer have analyticity and you have a D-bar problem. And there you have to use what I called guiding principle 2, which was about D-bar equations with small norms. Okay, so what's the end result? The end result is you can make statements assuming that R0 is in a Sobolev space like H1 plus 1, 1. So one derivative in L2 and one weight in L2. Okay, that's more or less what you need. And you need almost that much. You need a little bit less to do the scattering theory. So there's some wiggle room where you should do approximation, or what are they called? Embedding theorems. And in the case of the defocusing nonlinear Schrodinger equation, that's been done. Okay?
So there is, of course, a third way to handle the situation.
Uh-huh.
So this is a kind of nonlinear stationary phase.
Oh, thank you. That's right. Yeah. And I won't remember the person's name who was working that out most recently, but Varzugin, right?
But
Yeah.
also
Yeah.
two guys later, much later from
Uh-huh.
UCL.
Yeah. Okay. Thanks, Alexander. Right. Sorry.
For integrable systems, if you complexify X, would you get some information about the singularities of complexified CDE through?
Yeah. I think so. I don't have it. I mean, so short answer, yeah. The dependence on those parameters it's exactly whatever analyticity you have in those parameters. So like maybe one vaguely related statement is for Pan-Levé, when you choose to characterize Pan-Levé equations as the solutions of Riemann-Hilbert problems, right? Their analytic dependence on parameters is immediate, and the fact that the only thing that's movable is poles is also immediate. I learned that from the great book that Alexander and company wrote. But so it comes. You can get information about that from the Riemann-Hilbert problem. I haven't done anything like that of my own, but. Mm-hmm.
But do you analyze the kind of the quick, the fine structure? I mean, when you
In this last work, not yet. Yeah, there should be phase transitions in those. We haven't analyzed those yet at all. Yeah.
I think you mentioned you wanted to use this framework to study in soliton gas.
Yeah.
Is that something that you've already done, or is that?
No, I mean others have done lots of work on soliton gases with random initial data, and modeling the solitons by finite genus solutions, and then with randomness in those finite genus solutions. And it's sort of a combination of computation and analysis. And as far as I know, it hasn't been done analytically using just solitons. And no, I haven't done that. In those guiding principles? Okay. That's technical. But the question was about this. About that, right? So let's see. So you need something. So there has to be a parameter floating around, right? And the simplest statement is like if you know that the L2 norm on the contour is less than maybe 1 over t, for t is the large parameter. And you also need to know that the L infinity norm is less than 1 over t. And because I'm up here and have jet lag, I'm going to write down the L1 norm, even though I think that may follow from the L2 and L infinity norm. So if I have those three estimates, then I can prove that a solution M exists. And it's something like this. M minus the identity matrix is in the range of some Cauchy operator, which means you can represent it as a Cauchy transform of something, mu times like V minus the identity, over the contour, and the L2 norm of mu is less than 1 over t. And it existence and uniqueness. Yeah.
Any final questions before the 10th? Okay, could we thank Ken again?